Hi everybody, welcome to the next lecture on video coding, this time more on transforms. So last time we saw the DCT, the discrete cosine transform, and previously the DCT was defined as an ideal transform with unlimited accuracy. Remember, we have the cosine terms in it, and that's a float valued function. So basically it was assumed that we have the ideal cosine function, and we would like to approximate this function as closely as possible. But this has the problem that we have encoders with limited accuracy for the DCT and decoders with different accuracy for the inverse DCT. So we have different computational complexity or ways to compute the encoder side and the decoder side. So for instance, we have a more complex encoder, but then we have a more simple decoder, and then it doesn't quite fit, right? So this then actually leads to reconstruction errors from the different implementations. And this is actually not really necessary. Also, if we want to implement the DCT with low error, we need an algorithm with long word length. So we need an arithmetic with long word length and floating point implementation, which makes the implementation complex. Right, so maybe I should say with high precision. And low error. So that's basically a costly thing, and that's also not so good. So this is the problem for low-end processors, which makes the coder hardware more expensive. Since video decoding plays an increasing role in consumer hardware, where cost is very important, this problem was addressed in H.264, right? So they solved the problem by specifying the DCT with integer arithmetic, right? So now it's no longer assumed that you have float, but you have finite precision. So basically, every float number with finite precision can be specified as a fraction with integer numbers, and that's what's done here. So basically, instead of floats, we're using fractions for the integer DCT. And fractions can be specified as short integers, so we can spend fewer bits for the computation. Yeah, so in this way, the rounding errors that we make are known since it is specified in the standard. And in this way, we can still obtain perfect reconstruction in the absence of quantization, because in the standard we can specify the inverse DCT also with integer arithmetic, such that we obtain the exact inverse, right? So here, this is what we gain then. So we have limited integer arithmetic, but still we get the exact inverse. And that's possible, as we see in the following. So in this way, the rounding errors fit to each other to obtain perfect reconstruction. And in this way, we get a different transform, which is not quite the DCT, but only similar to it. But still, it has the same properties, and in the end, we get perfect reconstruction. So, good thing. So the approach here was to take the DCT matrix and multiply it with a certain factor and round it to obtain a transform matrix with integer entries. A factor which turned out to be suitable is this factor alpha equals 2.5, and you can also read more about it in Enrico Malva's paper on low complexity transform and quantization in H.264/AVC in the Transactions on Circuits and Systems for Video Technology in July 2003, which you can find within the TU Ilmenau network in IEEE-explore.IEEE.org. Yeah, so I recommend you to read this paper, and this basically was then becoming part of the standard. So it still leads to a good coding gain, this transform, but allows a low word length processing. So just 16-bit arithmetic. So that's good. So 16-bit is much shorter than, say, usual 64-bit floats. So the H.264 uses 8x8 and also 4x4 transform matrices. And here we look at the 4x4 version. We start with the usual 4x4 DCT type 2, and here we show 4 digits after the decimal point here. So this is the ideal DCT, at least with 4 digits after the decimal point here. And now we assume that we multiply our signal vector x from the right hand side. So we have y equals x times t to obtain the transform signal. So here y transposed here, because this should be a column vector, equals t times x transposed. And for the inverse, you get x transpose equals inverse t times y transpose. So that's the usual. So now we apply this mentioned factor alpha equals 2.5, and we get this here, right? So we take this matrix that we just saw and just multiply it by the 2.5, and we get these numbers. So we can compare it. Here, for instance, the first row was 0.5, and now the first row is 1.25. So 2.5 times 0.5 is 1.25. So the next step to obtain an integer implementation is to round it to obtain a useful transform matrix with integer entries. Right? This is what we have here in the next row. So now we apply the rounding function. And this is the matrix that results. So here you can see the 1.25 turns into a 1. The 1.6 turns into a 2, and so on. So now we have a matrix, very simple, just containing the numbers 1 and 2, and minus 1 and minus 2. So this can be represented with very few bits. So this is then actually the forward transform matrix used by H.264. We see that it is quite similar to the Walsh-Hadamard transform, where we only had ones and minus ones. But here we have additionally 2 and minus 2s. So yeah, but this makes a big difference because it gives a better compression performance. Malwa writes that for a stationary Gauss-Markov input with correlation coefficient ρ equals 0.9, the coding gain of the DCT, the original DCT, is 5.39 dB, whereas for this integer version it is 5.38 dB. So it's just a loss in the coding performance of 0.01 dB. So this is very little. And this is actually a good way to calculate the coding performance in a theoretical manner. So you just assume that you have some artificial input which has some similarity to natural images, this stationary Gauss-Markov process with correlation coefficient ρ equals 0.9. And then you obtain, you can compute the coding gain, and you obtain the coding gain in dB. So this is also an estimation about how many bits you can save when you do the compression. So the more dB coding gain you have, the more you save in bits for the compression. So this can be seen also here in the following. So this stationary Gauss-Markov input is generated using this simple structure. You have basically this infinite impulse response filter. You have some input x, which is noise in our case, white noise. And then it goes through this IIR filter, and this IIR filter just has one coefficient. So it takes the past output and multiplies it with 0.9 and then adds it to the next input. So here's the formula to it. Yn is equal x of n plus 0.9 times y of n minus 1. So this is the previous input. So really simple, and this simulates the fact that pixels are very similar next to each other. So here if you have an input, then the next output will be very similar to the previous output because of this factor 0.9. It just takes the previous output and adds it back to the input. So when you have a small input here, then the output consists of very similar samples. Yeah, and this is also what you usually observe in natural images, that pixels, neighboring pixels, are usually quite similar. Yeah, so here we have a nice mathematical model. X is some random memoryless Gaussian input, so a random number. So random number. And Y is the filtered output here, the stationary Gauss Markov signal. So in the Z domain we obtain a pole at Z equals 0.9, right? Remember, two-dimensional Z transform, in this case it's simply a one-dimensional Z transform. If we have an IR filter, then the coefficients appear as polynomial in the denominator. So that gives us a pole. In this case, it's really easy to see we have a pole at Z equals 0.9. So if you plug in Z equals 0.9, then you have 0.9 divided by 0.9, and you get the pole in the Z transform domain then. Right, so this fits to natural images because they also have a low pass characteristic. So basically this filter that we have is a low pass. When you have a constant input, the output grows. If you have an input which has changing signs, then it cancels. Yeah. But also observe that this is only a very crude and simple approximation of a natural image. But at least this gives us a simple model of a natural image. Right? It's easy to calculate. Then the coding gain is defined as the arithmetic average divided by the geometric average of the squares of the subband values, y square k, to give us an estimate of the compression performance of a given subband decomposition in dB. So the arithmetic average is our usual average as the sum of values divided by the number of values. The geometric average is using the product of and the nth root instead of the sum and the division by n. So here you can see it. Here is the arithmetic average, and in the denominator you have the geometric average. And you can also read more about it in this book by J and Null, Digital Coding of Waveforms by Prentice Hall. Yeah, so when we look at this equation here, in the numerator, the arithmetic average is the energy of our power of the signal. So Parseval's theorem said that the sum of the power of the subband signals is identical to the signal's power in the time or space domain. So here, this is what we got. So here, this is the power in the subbands, the average power in the subbands, and that's because of Parseval's theorem, this is identical to the power in the signal, right? So the original power. So if we now take the log of base 2 of the arithmetic average above, we get an estimate of the needed bits per sample in the time or space domain, right? Or times 2 since we have the square. And this is also called the entropy, right? So the log base 2 in principle gives us a crude estimate of the number of bits that we would need for an entropy coding. Right? It's also easy to see, for instance, if we have a number 7, then you know that it can be represented in 3 bits. Right? So this is basically how you can think of this. It gives you the number of bits that, or an estimation of the number of bits that you need to represent it using an entropy coder. So if we now take the log 2 of the geometric average, we can get an estimate of the number of needed bits per sample to encode the signal in the subbands. So you can see it. So the log 2 now in the term on the denominator. So here we see log 2 of this term here, then turns the product here into a sum and turns this square root of n into a division by n. And of course, inside the sum, we still have the log of base 2 of the y square of k. Right? So this is now the result for taking the log of the denominator here. And when you look at this term here, this log base 2 of yk square, this is an estimated number of bits times 2 because of the square per sample in subband k, and hence the sum is the estimate of the average number of bits per sample over all subbands. So this is the entropy over the subbands. Right? So here now you get an estimate how many bits you would need for the corresponding subband coda if you have n subbands. So now we have two estimations. One is the estimated number of bits for the subbands, and the first one was the estimated number of bits you need for the original signal. Right? So here the arithmetic average was, if we apply the log 2, then we get the bits per sample in the original domain, uncompressed. Right? So this is just applying then the entropy coda to our signal in the original domain. And here we apply our entropy coda in the subbands. And now it's interesting to see if we get actually a benefit from doing it in the subbands. And to estimate the benefit, that's exactly the coding gain. Right. So if we take the log 2 of the coding gain as defined above, we obtain the difference in the needed bits times 2 for the direct coding and the subband coding. So this is basically the difference between the direct and the subband coding. If you take the 10 times log 10, base 10, we obtain a number in dB where we have about 6 dB per bit. So this is the conversion now basically between dB and bits. And the usual is the coding gain in dB. So when you usually see numbers in dB for the coding gain, that's quite common. So we would like to have the coding gain as high as possible because then we benefit more from going to the subband domain. Yeah, so observe if the coding gain is 1 or 0 dB in the dB scale, all the subband values yk must be identical. Only in this case the geometric and arithmetic average become identical. Right? Maybe I should say must be. Yeah. So that means the more different the yk become, the higher the coding gain will be, with the extreme of a yk being 0. In this case we have an infinite coding gain. If we have a 6 dB coding gain, we save 1 bit per sample. Right? So if you calculate this number, 6 dB coding gain on average, then we get on average a saving of 1 bit per sample. And depending on how many bits per sample you spend, this can be considerable. So at least for this artificial signal, it is only a very small loss in coding gain of about 0.01 dB. So here you get a very small loss for this rounded DCT, or a cost of only 0.016 bits per sample. So not much. And that's good. That's what we want. That means we can do it. For a Walsh-Hadamard transform, the loss of the coding gain would probably be clearly higher. But again, it depends on the signal. But here we could actually calculate it for this simple signal. Observe that we can use the same approach with the same factor to obtain an integer 8x8 transform. Right? So that method works both times. So we still need an integer value for the inverse for the decoder. Is it possible to get an integer valued exact inverse? So it's not clear yet, right? So we first have to compute the inverse of our ideal DCT. right? And that's it. So here you have the inverse. So let's see, no, that's not the ideal, but H is actually the rounded. So here you can see it. Here's my H. So H is the rounded version. And now you can compute the inverse of this matrix and see what you get. Right, this is the exact inverse of the integer transform. So here we get it. And here we have again fractions, right? It's just a matter of how many bits do you need to represent it. Here we could use again a factor to obtain integer values for the inverse transform. In this way we would obtain the original but scaled with 2 factors. But the goal is to have factors as small as possible to have lower word length for the integer arithmetic. The trick here is to apply different factors to the columns and allow factors which can be implemented with a shift operation. Here factors 0.5. Yeah, and the factors are used are 4, 5, 4, 5. So with these factors, we multiply those factors to each of those columns. We get this inverse, this modified inverse here. So here we can see it. So the exact inverse would be the modified inverse times the diagonal matrix, which contains those factors on the diagonal. Right. So if you multiply the first column with 1/4, then we have the first column for the exact inverse. Next column we multiply it with 1/5, then we get the entry for the exact inverse, and so on. Right, and this also shows now we have a really simple modified inverse matrix. It's just 1s and 0.5s, plus minus. So really easy. So the 0.5 can be implemented with a shift, and 1 is basically no operation, and the minus is just a sign change. So really easy. And also this diagonal factor here can be easily implemented. So you could then in the decoder, after applying the inverse transform, you just apply these inverse factors, and you can actually absorb them into the dequantizer. So then the dequantization would be one step together with those factors. So really easy. So this shows that we just extracted the diagonal matrix from the inverse. The diagonal matrix does not need to be computed explicitly because we can factor it into the inverse quantization of the decoder. Remember, reverse, it's not actually inverse, reverse quantization. There we basically take the index, quantization index, and multiply it with the rounded, we multiply it with a step size, the quantization step size. So that's the number. And if you multiply the step size by the corresponding entries here in the diagonal, then we have just a new factor. So it's actually no additional multiplication necessary. Right. So in this way we obtain the exact inverse with very simple numbers or fractions, which are easy to implement. So here's an example of a fast implementation. So this is the forward transform. Here you have the x, and you can see here's a sign change. Here you have factors of 2, and after some additions you get the result. So this is then the 4x4 integer DCT. Similar for the decoder. Here you have the subband values, you have some multiplications with 1/2, some sign changes and some additions here, and then you get the reconstructed. So really easy and very efficient to implement. Yeah, and for the coding of the signal, we have to take a look at the dynamic range of values after the transform, because that also affects the word length and the number of bits. So important for the fixed, this is important for fixed word length integer arithmetic on the CPU that we use for encoder and decoder. So assume we have an input signal with maximum value of A, given by the word length. For instance, an image with brightness levels A, for the worst case, this would be the maximum value. For instance, when you have an image, a luminance image, then A goes from 0 to 255, right? So then A would be 255 maximum, corresponding to 8 bits. Then we have a signal vector containing the values plus minus A. So if we have chrominance values, we have then the values between minus 127 and plus 127. So again, coming from the 8 bits, which is here multiplied from the right hand side. Right. If we take the transform matrix H from last time, and if one column X, for instance, is the vector A minus A minus A, so this is the worst case to get the largest output, then the multiplication with the second row of H results to 6A. Right. So when we look at A again, so here first half is positive, second half is negative, and going up here, so this is your H, and we multiplied with the second row, which is this one here. Here you can see you have 2A, 1A, so this is 3A, and here we have the sign change, which compensates with the sign change in the signal. Then we have another 3A, so the total is 6A, and it turns out this is the largest that you can get using this matrix, 6A. Right. Yeah, so this is the maximum for this matrix. If we then also transform the rows of our image, we get a maximum value of 6 times 6 times A, so another factor of A, of 6. So then we get 36A. This means that the dynamic range we have for our subband coefficients is increased by this log base 2 of 36, which is 5.17 bits. Right? This factor translates into in additional bit requirements. We need 5.17 bits more than the original 8 bits. Right? So instead of 8 bits, the output would need to be encoded by 8 plus 6, which is 14 bits. Right? Because we need to round up. Yeah, so rather 6 bits more for fixed word length integer arithmetic. So this is an overhead which we need to provide in our coding signal processor. This is also a reason why we wanted to have our factor alpha as small as possible, to limit this factor here. For the inverse matrix in the decoder, the factor is somewhat smaller. Here we get a factor of 4, leading to a factor of 16 for the rows and columns, and hence 4 additional bits for the dynamic range for the decoded subband samples. Observe that this also means a reduced maximum information content in the subband signals, which is the result of the quantization in the encoder. Yeah. So these effects become important if you want to implement our algorithm with integer arithmetic with limited word length. So H.264 is made such that it can be implemented with 16-bit arithmetic in the encoder and decoder, and which is sufficient, as can be seen here. So we saw in the encoder we need 14 bits, in the decoder we need 8 plus 4, which is 12 bits, so 16-bit is sufficient. Right. And 16-bit is kind of a standard for cheap hardware. Right. So this enables the implementation into cheap hardware. Yeah, so here you can find on the literature again. Here's the book by Jay and Noll, which I can highly recommend. It's out of print, but you can still buy it or get it or lend it from the library. Digital Coding of Waveforms. Then here this article which I mentioned by Malva et al. Low Complexity Transform and Quantization in H.264/AVC in the Transactions on Circuits and System for Video Technology in July of 2003, which you can get from our IEEE Explore. And there's also this paper on the H.264 video coding standard in the IEEE transactions on multimedia from 2006. So there you have an overview of the standard. Similar here, this is a paper on low complexity video coding standard and the emerging HEVC standard from the Picture Coding Symposium in 2010. And here's a paper on high performance, low complexity video coding and the emerging HEVC standard in the IEEE transactions on circuits and systems for video technology from 2010. And here is one from Heinrich Hertz Institute in Berlin. Video compression using nested quad-tree structures, leaf merging, and improved techniques for motion representation and entropy coding in the IEEE transactions on circuits and systems for video technology, also from 2010. So all can be obtained from IEEEexplore.IEEE.org inside the TU Ilmenau network. Okay, so this should be it for this part. Thank you for your attention, and then see you next time.